Have you ever seen a flash of lightning tear across the sky and then counted the seconds until you hear that deep, rumbling boom? It's a classic sign of a storm, but what's actually happening up there to create such a powerful light and sound show? Well, today we're pulling back the curtain on the sky and cracking open the incredible science behind thunder and lightning. It all begins inside those massive, towering storm clouds you see on the horizon. Imagine a giant storm cloud, a cumulonimbus cloud, stretching miles up into the atmosphere. Inside, it's a chaotic world. Warm, moist air is rushing upwards, while cooler, denser air is sinking. This constant churning motion sends water droplets and tiny ice crystals crashing into each other. Think of it like a colossal washing machine tumbling around in the sky, a whirlwind of water and ice. This constant, frantic motion is the engine that drives the storm. Now, all of that bumping and grinding between the ice crystals and water droplets ISNT, just for show, it acts like static electricity on a grand scale. As these particles collide, they exchange electrical charges. This process, called charge separation, starts to create distinct electrical zones within the cloud. Generally, the smaller, lighter ice crystals, which tend to be positively charged, get carried upwards by the rising air currents. The larger, heavier water droplets, or hail, which are typically negatively charged, sink or get suspended in the lower and middle parts of the cloud. So, what you end up with is a massive natural battery. The top of the cloud becomes positively charged, while the bottom of the cloud accumulates a strong negative charge. But the cloud isn't the only thing involved. As this powerful negative charge builds up at the base of the storm cloud, it has a profound effect on the ground below. The negative charge in the cloud repels the negative charge is the electrons on the surface of the Earth. It essentially pushes them away, leaving the ground directly beneath the storm with a net positive charge. So now we have a classic electrical setup, a massive negative charge at the bottom of the cloud, and a corresponding positive charge on the ground below. The air in between acts as an insulator, but there's a limit to how much electrical pressure it can withstand. This difference in charge creates a huge electrical potential, a powerful tension between the sky and the Earth. When this electrical difference, this voltage, becomes too great for the air to insulate, nature needs to find a way to balance things out. The atmosphere can no longer hold back the immense energy, and that's when it happens. The built-up energy is released in a spectacular, explosive discharge of electricity, a giant spark that we call lightning. It's nature's way of saying, let's fix this imbalance, and it does so with incredible force. Now, a lightning strike is onto as simple as a single bolt just zapping from the cloud to the ground in one clean motion. It's actually a much more complex, step-by-step process. It usually begins with a faint, invisible channel of negative charge descending from the cloud. This is called a stepped leader. It snakes its way down towards the ground in a series of short, branching steps, searching for the path of least resistance. As this leader gets closer to the ground, the positive charge on the surface reaches up to meet it, often through tall objects like trees, buildings, or even people, in the form of an upward streamer. When the downward-moving stepped leader finally connects with one of these upward-reaching streamers, the circuit is complete. And that's when the real show begins. A massive surge of electrical current, the return stroke flashes brightly as it races back up the channel from the ground to the cloud. This is the intensely bright flash that we actually see as lightning. It happens in a fraction of a second, but it's incredibly powerful. In fact, this return stroke heats the air in the lightning channel to temperatures hotter than the surface of the sun, we're talking about up to 50,000 degrees Fahrenheit, or about 27,000 degrees Celsius, all in a tiny moment. So, we've explained the lightning, but what about the thunder? Well, the thunder is a direct result of that intense heat. When the air around the lightning bolt is superheated so suddenly, it expands explosively, much faster than the speed of sound. Immediately after the flash, the air cools down just as quickly and contracts. This rapid, violent expansion and contraction of the air creates a powerful shock wave, a massive disturbance that ripples outward through the atmosphere. This shock wave is a sound wave, and what we hear on the ground is that sound wave thunder. So, in simple terms, thunder is just the sound of air getting slammed and snapping back into place by the energy of lightning. This explains why you always see lightning before you hear thunder. Light travels incredibly fast, at about 186,000 miles per second, so the flash reaches your eyes almost instantaneously. Sound, on the other hand, travels much more slowly, at roughly 1 mile every 5 seconds through the air. So, after you see the flash, you can actually count the seconds until you hear the thunder to estimate how far away the storm is. For every 5 seconds you count, the lightning is about 1 mile away. And because we're talking about the power of storms, a quick but very important safety note is in order. Thunder is your natural warning system. If you are close enough to hear thunder, you are close enough to be struck by lightning. It's as simple as that. The moment you hear that rumble, it's time to seek proper shelter. The safest place to be is inside a substantial building or a hard-topped metal vehicle. Avoid standing under isolated trees or in open fields, and stay away from water. Lightning is beautiful and scientifically fascinating, but it's also incredibly dangerous. It's crucial to respect the storm and prioritize your safety. So from the chaotic dance of ice and water inside a cloud to the buildup of massive electrical charges and finally to the explosive release of energy that creates a superheated channel of air. Now you know the full story behind thunder and lightning. It's not just a random boom and flash. It's a stunning display of atmospheric physics at work. We hope this journey into the heart of a storm has made them a little less mysterious and a lot more amazing. If you enjoyed geeking out about the science of weather with us, do us a favor and hit that like button and subscribe to the channel for more deep dives into the world around us. Coming up next, we're relieving the skies and traveling into our own minds to explore the weird and wonderful world of dreams. You won't want to miss it. Thanks for watching.